An analog natural logarithm calculator is just shown and designed here using 4 ideal op-amps and 2 ideal diodes. We want to show that this circuit nicely realizes V out as a function of a natural logarithm of V in divided by control voltage, which is a constant voltage here. The nice thing about this circuit, if we can prove this, is it enables computation of the natural logarithmic function with minimal dependency on, let's say, thermal variation. So sensitivity to thermal variation is reduced via the difference of the 2 diodes that are inserted in this circuit. Okay, so how does this work? First thing is make the assumption that the supply voltages of all the op-amps are properly connected, positive, negative supply, and the op-amps are all of them are in linear region of operation with dominant negative feedback. So virtual short is valid for all the op-amps, which means the voltage at positive input terminal equal to the voltage at negative input terminal for all the op-amps, which means if on op-amp, let's say 1 here, we have 0 on positive input terminal, then for negative input terminal, we have 0 as well. If for op-amp number 2 here, we have VC or voltage control at positive, then we have VC at negative, and then VC we have at the output. Basically, this op-amp here is just simply a buffer because it doesn't do anything except buffering the input voltage, and input voltage appears at its output. Okay, the thing is, I'm going to show you that this second stage here with op-amp 3 is just working as a current source, and it will inject a current source through the circuit which we refer to as I2, and that's going to simplify the whole process. That current cannot go through the positive input terminal of ideal op-amp number 4 because it's ideal op-amp with infinite impedance at input. So all the current that is coming out is going through the lower branch downward toward, let's say, diode number 2, resulting in a voltage drop like this, VD2. At the same time, I1 from the input caused by V in is flowing inward, and we can say the value of I1 is equal to V in divided by let's say R3. The reason for that is we have V in and 0 on the 2 sides of R3. So voltage drop across R3 is V in, hence the current I1 is V in divided by R3. Let's refer to this as equation number 1. This current I1 has to go completely through the diode because it cannot go other way. It cannot go through the input. And it will result in a voltage drop VD1 across the diode number 1. Now, the nice thing is, since we know that the voltage here is 0, we can just say there is a plus minus drop here, and then again minus plus add to get to this node, which is important for us, and we're going to refer to that as voltage V2. I need V2 because as soon as I find it, because of virtual short, then here is V2 as well, and that will get me to the output easily. So let's find V2 first. V2 is equal to, of course, as you can see, we have 0 here clearly, so we have 0, and then plus minus VD1, so it will become minus VD1, we are going lower, but then we are going up again via VD2, and we get to V2. So we are going this way, basically, to get to VD2, voltage-wise, like a KVL. Okay, that's one thing to remember. I'm going to substitute for VD1 and VD2 using the current voltage equation of ideal diode, and that is something well known. So to do that, I'm going to just write it one time here. So we know for ideal diode, so for ideal diode, or close to ideal diode, we have the current of diode is equal to, so let me write it clearly, the current of diode equal to saturation current of diode, and then e to the voltage across the diode, divided by eta, which is the ideality factor of diode, Vt, which is the let's say thermal voltage. So this eta is the ideality factor, which means how ideal the diode is, and eta is a number between 2 and 1 for germanium diodes that are closer to ideal diode, it's close to 1, and for silicon junction diode, it's closer to 2. And VT is the thermal voltage of diode, thermal voltage, and it's usually around, I think at room temperature is around 25 millivolt. Depends on exact temperature, but VT's formula, which we're not going to deal with, is just K times T divided by Q, in which K is Boltzmann constant, T is the temperature of the junction of diode at in Kelvin, and Q is 1 electron, and it's in Coulomb, so roughly about 1.6-ish times 10 to the minus 19 Coulomb. And when you compute that, it ends up to be somewhere in the close to 25 millivolt at room temperature. Okay, so at room temperature. Now, IS is the saturation current. It's a small current, but when multiplied by a large number resulting from this exponential function, then you would get a sizable current for the current of diode ID. Now, what's the reason we talked about this is because as soon as you have this, what I can say is take a natural logarithm from both sides of this equation, and naturally we get voltage of diode. Let's say voltage of diode VD1 is equal to eta VT natural logarithm of the current of diode divided by saturation current. And remember that saturation current is very, very sensitive to temperature and many other factors. The nice thing about this circuit is I'm going to show you that with the two diodes shown like this, we can get rid of IS, and therefore the dependency, a lot of dependency on temperature via IS. So let's now use this equation, which I'm going to refer to as equation 2, and apply it to here, which is equation 3, and just substitute for voltage of diodes. So I'm going to use equation 2 and 3. So equation 2 and 3, and as a result, I am going to get V2 is equal to negative, and negative VD1 is negative eta VT, so let's factor eta, negative eta VT, and then we have ln, so natural logarithm of ID1, which is simply for the first diode, I1 is flowing, so just write it I1, divide by IS, and for the second diode plus VD2, well, we are factoring out a negative sign outside, so as a result, we're gonna have negative natural logarithm of I2 over IS. So now simplifying the whole thing, and let me move this to here so that we have enough space. So now we get negative eta VT ln, or natural logarithm of I1 divided by I2. Very nice. So this is what I am interested in terms of using. Let's refer to this as equation 4 for V2. I have I1 here, right? So I previously calculated I1 here. The only thing I need to find is I2. And you can see that now V2 is found to be just a function of the ratio of I1 and I2. There is no appearance of IS, and that's a very good news I was trying to tell and say that we're going to get to it via this circuit and get rid of IS. Okay, so for I2, or the current coming out of this current source here, so there is a current source shown here. The I2 is coming out of it or going into it, depending on whether it's sinking or sourcing current. So that I2 is simply this current I2. This current I2 that I'm showing here is simply computed like this. I'm going to show, let me use a different color so that I can highlight what I'm trying to show. The voltage drop across this 100 R2 resistor, which is something like this, assuming a current is flowing this way, and of course no current can go through through the input terminal of op-amp, so is the same voltage drop across these two guys combined together. So I'm talking about this voltage drop. So plus minus and then plus minus. Let's say a current is flowing this way, and let's just refer to voltage here as Vx, and as a result the voltage here as Vx as well. Because of virtual short, the negative and positive input terminal should have the same voltage. Now what I can say, as a result, I can say the voltage of 100 R2 resistor on top should be equal to the voltage of R2 resistor bottom plus the voltage of 99 R2 resistor bottom. So let me substitute for these values. The voltage 100 R2 is simply 100 R2 times its current. But its current, as I said, is the same current that is going through R1. So whatever current is coming out of is going through R2 has to continue to R1. But the nice thing is we have Vx on one side of R1 and we have Vc on the other side. So that current is simply Vx minus Vc, or control voltage, divided by R1, equal to VR2. If there is a current that is going this way, again cannot go through the input of op-amp. That current is simply Vx divided by R1, because the other side of R1 is 0, so the plus minus across R1 is simply Vx. That current has to also go through R2 in addition to I2 that is also going through R2. So effectively what I can say is, on the other side of this equality, I have the current Vx over R1 that is going through both 99 R2 and R2, so 99 plus 1 R2. And also I have the current I2 that is going to R2, so it will be I2 R2. So it will be, let me shift it so that you can see it. Too tight here, so there you go. Okay, great. So I have I2 R2. Great. What is the benefit of writing this way? Well, immediately we can see the benefit. The benefit is, let me just put it this way. If I clean it up so that you can see, Vx divided by R1, and then we have negative 100 R2 over R1 times V control equal to 100 R2. So I am dealing with this portion, which is 100 R2 over R1 Vx, and then plus I2 R2. Well, the nice thing is, as you can see, this portion cancel out this portion. So as a result, I get simply I2 R2 equal to this value. So I2 R2 equal to that. Therefore, I can say I2 is simply minus 100, and R2 also, you can just remove it from both sides, so it becomes minus 100 over R1 Vc. That's very nice. That is super interesting. So I'm going to name this as equation 5. And we're almost done, because what happens is now I'm going to use everything I have. I'm going to use equation, let me also write it with different colors so that it will be visible which one I'm referring to. So remember, this is equation 4 here. So we refer to this as equation 4. So I am going to use equation 4 with the substitution for I1 and I2 by 1 and 5. So I get V2 equal to, let me also change the color here back to what we had. So I get V2 is equal to, back in equation 4, see, V2 is equal to minus eta Vt, and then natural logarithm of I1 is V in divided by R3 times and then divide by I2, which is keep the minus here, and we have say 1 over I2, which means R1 over 100 Vc. Almost there. Almost there. And last thing is, we have to just deal with the last stage, which is a simple non-inverting amplifier stage. That's it. This is a non-inverting amplifier. And for this simple non-inverting amplifier, we know that Vout is simply R1 plus R4 divided by R5 times its input, which is V2. I mean, it's just a simple voltage divider. Because of virtual short that appears on the positive terminal, the fact is virtual short, because of virtual short, V2 that is on positive terminal should appear at negative terminal as well. And because of that, then we can say then 1 plus R4 divided by R5 times V2 should appear at the output, which is Vout. That's why I'm saying Vout is equal to 1 plus R4 over R5 V2. Now, using these two things we found, because we just found V2 as a function of V in and R1, and then Vout as a function of V2. These two together will get us what we needed to prove, which is exactly the formula written on top, which means this formula. So Vout is negative eta Vt thermal voltage natural logarithm negative, and of course 1 plus R4 over R5 natural logarithm of negative R1 divided by 100 R3 times V in divided by control voltage, or Vc. I hope that this example is helpful in terms of illustrating a practical design or near practical design for a logarithmic calculator or computer which computes the natural logarithm, of course in a reasonable range, as long as the op-amps are kept in linear region of operation, and it shows how we can properly design to reduce the sensitivity to thermal variation.